Good morning or good afternoon, ladies and gentlemen, even good evening, because I know some people are joining from India and Asia Pac, and it's quite late over there. Whether it's the first time you join us in one of our online sessions or you're a regular, I would like to welcome you to this one session that is very, very exciting. If you guys have been following any of our latest sessions, in any of the markets, you will always hear constantly the PV plus battery setup. This is a big issue developing in nearly every single market that we cover. It is the future. It's clear everyone says that batteries are the future and the dispatchability of PV is the future. And we're here today to get into the crux of how to design the systems, how to make them work for you today. We have two super experts, worldwide experts with us today from two companies. We have Vikas from Stirling Wilson and we have TJ from Fluence. And they're going to give you a lot more detail into how these work, how you have to think about them, and how you can put them into your plans. So Vikas, can you introduce yourself very shortly and tell us about you, your company, and where you're joining from?
Thanks a lot, Belen. Good evening, everybody. I'm Vikas Bansal. I'm joining you from Dubai today. I head the global business development for Stirling and Wilson for solar and storage department. Stirling and Wilson is the largest solar EPC in the world. Apart from solar EPC, we are also offering solar plus storage solution. I really look forward to this webinar today. Thank you.
Thank you very much, Vikas. And TJ, please, the same to you. Can you introduce yourself, your company, and also where you're joining from?
Sure. Hello, everyone. My name is TJ Winter. I'm with Fluence Energy. My title is essentially I'm the product manager for Fluence Energy. And for those of you who may not be familiar with Fluence, we're a new company. We're a joint venture between AES and Siemens, and we're the world's leading energy storage solution provider. So really, I'll be bringing that energy storage perspective into this discussion. Thank you.
So if you guys have been in any of our last webinars, you would have heard that Fluence has about 50 projects at present, working on 50 projects at present. So there is a lot of stuff that they can tell us. And, obviously Stirling and Wilson have been working in all sorts of developments, and they also have a few PV and battery projects that they're going to talk to us about. So before we continue, this is how it's going to go today. Super simple. First, Vikas is going to talk and give you a little bit speech. Then TJ, their perspective, each of them. Then we're going to take a questions and answers section, which you can use the little Q&A box at the bottom. Before you ask me a million times, because I know you will ask, we are recording this session and we will have the PDFs available, which we will send to you. So you don't have to worry, you will not miss a thing and you'll be able to review it thereafter. So, Vikas, can you please share your screen with us and get ready? And whilst Vikas is doing that, just please do us a favor. I'm Belen and I'm joining from Madrid today. Vikas is in Dubai and TJ is in Pennsylvania. What about you guys? Where are you joining from? I know there are people from everywhere, some people from Mexico I've seen already. I've seen some people from India. So where are you at the moment? And let's just get the conversation started. And this is definitely going to be a fantastic presentation. There is a lot of interesting information that you're going to learn today. So Vikas, can you put that in large screen?
All right. Can you see the screen?
Perfect. Off you go.
All right. Before we go into the presentation, a couple of more lines about Stirling and Wilson. Stirling and Wilson has installed almost 2.5 gigawatt of solar PV in the last 5 years. We are building about 5 gigawatt plants all over the world, including US. We also have got about 1.8 gigawatt of gas-based power plants and 4 gigawatt of diesel-based power plants. So put together, we're talking about an 8 gigawatt portfolio. Right now, we are ranked second in the world in solar EPC. So what do we do? Basically, we offer dispatchable solar power. So we do EPC plants which have the capability to give you power which is constant, which could be 24/7, which you could control. Okay, so coming to the topic here, so we need to understand why does solar need energy storage. So for the last 1 decade, solar has been using grid as a dump yard, literally. So whatever you produce, whatever time you produce, just dump it into the grid. Till now, the question was how cheap you can do it. As long as you are able to do it competitively, as long as you are able to bring down the cost, you were all fine. But when you talk about the condition of the grid for the last few years, now we are getting into a debate whether the grids are able to take solar anymore. Can they take 30% solar, or wind for that matter? Can they take 50? And if you look at the load curve for the entire grid, right now we are in a situation wherein if you look at the evening time, the ramp up rate for the for the conventional power plant has to be very, very high if they have to still maintain the grid. So solar could work from 9 to 5 or 9 to 6 in the morning. All the conventional power plants, gas, diesel, coal, they have to work at a very low efficiency, low PLF. But in the evening, we expect them to absolutely ramp up, which is not fair, right? You can't be using everybody else to your advantage. So we strongly believe that in the coming 1 or 2 years, all the governments, all the developers, all the grid operators, they're going to ask for more firmness in the solar power. They will want all the developers to add certain storage to solar to make it more firm. And at the minimum, the solar power plant should have the capability either to handle the peak or to control the rate of power which it is injecting into the grid. Okay, so now that we understand that the solar power plant has to have some dispatchability, some firmness, let's look into various components which you need additional to the solar PV plant. So number one, you need an HVAC system for energy storage. All of these batteries, they produce a lot of heat. If you're not getting a heating, ventilation, air conditioning system with the battery from the battery supplier, you have to design your own. It's not very tough. It can be done. You have to buy bidirectional hybrid inverters, which is basically your charge controller, something which can charge the batteries and discharge the batteries. You have to go for the energy management system. So this piece is the most important piece in the entire solar plus energy storage plant. It can control solar inverters. It can control the charging and discharging of the batteries. It can control the dispatch strategy of the energy storage system, which is very, very important. It can ensure the compliance of the entire plant to the grid requirements. Now we are seeing that a lot of grids, especially in US, Australia, they are coming out with very stringent requirement in terms of the technical parameters of the grid. So if you have a rugged energy management system, it can ensure that you are always complying to the grid. And then you obviously need to have AC side of infrastructure. You need to have a transformer to evacuate your power. You need to have HT panels. So these are the basic things. All of these things are already existing in the market, fairly proven. But the entire system is dependent on how well you marry all of them. What is your strategy on the design? So when we talk about the design strategies, there are a couple of configurations which we can follow. We can follow a very typical configuration, which everybody seems to be doing nowadays, which is coupling the solar power plant and the storage system on the AC side, which means that you have a normal solar power plant evacuating at 33 or a 132 kV level. You have a energy system with a hybrid inverter, again evacuating at a 33 or a 132 kV system, and they talk to each other at the AC level, which means that you are going to convert AC to DC 2 times, which means you are losing almost 5 to 7% more as compared to the other system. But if you talk about the flexibility, AC side coupling gives you a very high amount of flexibility. You can design the system as per your requirement. You can increase or decrease the system. System becomes more modular. The system is very reliable because all the equipment which are being used, they have been tested and tried for the last many years. It's a highly reliable system. But at the same time, as I said, you are adding an extra cycle of conversion, so you are losing 5 to 7% of the energy. Now let's come to the DC side. There is a DC side coupling which is possible, which essentially means that you produce power from solar. Instead of converting it into AC, you use a DC to DC converter and you straight away charge your batteries. On the face of it, it looks to be an obvious solution. Everybody thinks this is the way it should be. It will help you to increase AC-DC loading of the system, which means the balance of the system cost comes down, but things are not that simple. If you go to the market for a typical DC to DC converter, which basically converts X volt of DC to Y volt of DC, the price is very, very exorbitantly high. If just to give you an example, if you are able to buy a normal inverter for X dollars, the same sized DC to DC hybrid inverter will cost you 3 to 4x. So you're talking about a huge price adder here. That's one. Second downside is you have very less flexibility to design the system. Since you only have one inverter which is evacuating the whole power, you cannot design the system where you want. You have limitations on the design. So where do we stand? If anybody is very clear on the use case, if you are very, very clear on the application which you are going for, if you are very clear that you're not going to change the use of that application, you may consider using DC side coupling. The cost of the equipment is going to come down. But if you're looking at a system which is more flexible, you may change your strategy after 2 or 3 years. You want to add more in the future, you should go for the AC side coupling. Moving on, what are the other design strategies which are typically deployed? I will talk about a very interesting topic of peak power clipping management. So whenever we design a solar plant, we always put more DC and we put 20 to 30% less AC in order to optimize on the system design. But a lot of time we are not able to put high amount of DC power solar panels because it results into clipping of power at the inverter level. Just to give you an example, if you load your system by 35 to 40% in a typical place like Dubai, your clipping loss could be as high as 1 to 2%, which is a lot of energy, especially we're talking about big plants here. So what do we do? In this case, we can, for that duration, we can calculate the amount of batteries you need. It could be a lithium ion or it could be a advanced lead acid battery. For that duration of time, rather than solar plant losing the power, we charge the batteries. All the excess power goes into the batteries, and during the evening time, 4 o'clock or 5 o'clock, when the radiation levels are low, you can put that power back into the grid. So what have we achieved? We have been able to put more DC for the same AC, which means the levelized cost of electricity is less. You become more competitive. Whatever energy you would have lost in an ideal scenario, you are not losing that energy and you are able to generate revenue out of that energy. So that is one of the design strategy which could be deployed. Second, so nowadays, whenever we size our inverters, we always have to be very careful about the reactive power compensation. All over the world, be it Middle East, US, Australia, or for that matter, India, all the grid operators are now very, very particular on the reactive power compensation, which is one of the most important designing parameters. So if you're going for a plant with storage capacity, if you're going, let's imagine you're going for a 100 megawatt solar power plant and you have a 10 or 20 megawatt of storage, for which you'll be putting 5 or 10 megawatt of hybrid inverters. The same inverters could be utilized to meet reactive power compensation for the grid. What does it mean? It means that when you are designing your solar plant, rather than designing your solar plant for a higher capacity of inverters to meet the reactive power of the grid, you can utilize the hybrid inverters and you can reduce your cost on the solar side of it, which overall means that your levelized cost of electricity goes down. This is the second strategy. Third strategy is, rather than when you couple your energy storage with solar, rather than going for a separate transformer, you can oversize the transformer which is being used for the existing solar power plant. The same transformer could be oversized which is less costly, and the same transformer could be used to inject power in the grid. So these are the typical, strategies which are being used to optimize LCOE of the entire system. And obviously there could be more strategies, but as I said, designing a solar power system with storage is very highly dependent on the use case. So there could be a use case wherein one design strategy may work, but there could be a use case wherein the same design strategy may not work. So it is highly flexible, it is highly customized solution which one has to design for such systems. So moving on. So Stirling Wilson has been doing many projects in the last few quarters. We have picked up many hybrid orders, which have got solar, which has got diesel, sometimes batteries. I'll talk about a very interesting project which we are doing in Nigeria. In Nigeria, we are powering 3 universities. Totaling, we are putting about 5 megawatt of solar power. All of these universities will have diesel generators because the grid is very unreliable in that part of the world. And this plant has a very unique feature. We are putting advanced lead acid batteries. We are not putting lithium ion batteries for the commercial reasons. And we are ensuring an autonomy of 1+1 day, which means the entire system can work without sunlight for almost 2 days with a very minimal use of a diesel genset. So till now, all of these places are very remote. If I have to talk about a location, all of these places are almost 200 to 500 kilometers from the Nigerian capital. So we are talking about very remote locations. So Stirling Wilson is going to maintain these systems for almost 10 years. So what have we achieved? When this plant gets over, number one, all of these universities will have 24/7 power without grid, with minimum use of diesel genset. And after our evaluation, we found out that we would be reducing the cost of power, which primarily used to be diesel, by more than 40%. So they were paying almost $30 to $35 of dollar cents per watt per kilowatt hour for the power till now. With this system, their cost will come down to almost 15 to 16 dollar cents, which is great for them. So all of these students put together, these 3 universities, they have got about 5,000 students. So all of these students will now have reliable, almost green power, and they will be saving on cost too. So yeah, so that's all, ladies and gentlemen. Thanks a lot for listening to me. I will hand it back to Belen.
Thank you very much, Vikas, and thank you for your presentation and for sharing so quickly. TJ, now it's your turn. Please share your screen, and we have a few questions that we'll ask right after TJ gives his presentation. By the way, he's been answering some of your questions already, so he's been busy, TJ. But we'll take it from there. Perfect. Just make that large for us. Perfect. Great. You're ready. Off you go.
You can hear me?
Yes, great. Absolutely.
All right. Well, thank you, Vikas, for that. I'll touch on some of the same themes as you, but also I think expand on some of it a bit as well. So first, I'd like to give an introduction about Fluence. So Fluence is the global leader in energy storage. We have a global footprint. As I mentioned during my introduction, we are a joint venture between Siemens and AES. And together we have over 10 years of experience worldwide with projects in 16 countries. That's 60 plus projects with over 500 megawatts deployed and operating of energy storage. And really, the reason that Fluence brings to the table with Siemens and AES coming together are really 3 things. The first is the experience. You won't find more experienced people to work with in energy storage. AES and Siemens were both early pioneers in the industry and have done quite a bit of work in the last decade on it. We also bring scale, both in design and engineering and procurement and customer service global with our new joint footprint. And then we really understand also the fit with the particular customer needs, because we come from this both electrical OEM background as well as the developer background. It's really a unique viewpoint that we bring to the energy storage world. So with that introduction, onto the topic. As Vikas was touching on, the opportunity for renewables with storage really depends quite highly on what problem you're trying to solve by adding storage to your renewable system. And so there's a couple of different ways to think about this. I've highlighted one particular way to think about it here, which is to separate it into 3 separate use cases. The 2 use cases on the left, which I'm calling grid services and renewable plant stability, are sort of separate sides of the same coin, you could say. And that grid services is really about being able to help the grid take more renewable energy penetration as the amount of solar and other renewable penetration increases on the grid. The second side of sort of a similar type of use case is providing more stability to the renewable plant itself. So reducing voltage stability issues, reducing renewable energy curtailment issues. But really both of these, the theme for these, one of them is grid services is more like trying to help the grid. Renewable plant stability is trying to help the project, right? If you want to think about it that way. But both of them, the focus is really on solving some of these issues as more and more photovoltaic goes onto the grid. And the amount of storage that you need for these particular type of use cases is towards the lower end of the duration scale. So I'm showing here 30 minutes to 1 hour for grid services, 30 minutes to 2 hours for renewable plant stability. The third use case, which I'm highlighting on the right side of on this slide, is increasing that amount of renewable penetration with renewable firm energy. So here, what you are essentially doing is taking some of the PV energy which is produced during the middle of the day, and you're essentially making the facility dispatchable by time shifting that energy into other parts of the day, typically late afternoon or evening as the load comes up. But you could time shift to other times as well if there's a reason for you to do it with a particular opportunity. And to do this particular use case, you would need essentially more battery. So within the 1 hour to 8 hour range of battery duration is what I would expect to be typical for a renewable firm energy use case. As we touched on briefly earlier as well, storage can be either AC coupled or DC coupled with the solar. This is a bit of a cartoon drawing of those 2 particular options, sort of a cartoon one line, if you will. On the left is the AC coupling, where both the solar and the battery have their own dedicated inverters and are connected at some point further up towards the grid. So as was alluded to earlier, exactly where that connection is, you can vary that around a little bit. You could have both the solar and the battery connect at high voltage, or you could actually have them connect at medium voltage and then have only a single transformer between the medium voltage and the grid. But the main takeaway here is that the solar and the battery both have their own inverter converting these DC sources into AC. The DC coupled architecture, which I'm highlighting here on the right side of the slide, means that the solar and the battery both go into a common DC bus on the inverter before going to the grid. And so in order to integrate that electrically, additional DC to DC unit needs to be placed between the battery and the DC bus of the inverter so that the voltages line up, as was mentioned earlier as well. And these particular solutions have some advantages and disadvantages. I'd like to touch on my own view on that a bit as well. So how do you decide if DC coupling is the right choice? As Vikas mentioned, the AC coupling is sort of the conventional or the traditional way of doing this, of thinking about this, but DC coupling is a new hot topic, and it really does offer some benefits, but it may not be right for every project. So here's how I would think about that. So first of all, energy generated by the solar project and time shifted, you can do that with either AC or DC coupling. That's something that's the same for both. The next topic is something that is unique to or specific to the United States, but that is the eligibility for the investment tax credit. Actually, both AC and DC systems can be eligible for this ITC. There's a bit of a misnomer that it must be DC coupled in order to capture this, but it can be either AC or DC coupled, though in either case, you need to demonstrate that at least 75% of the battery charging is coming from the PV source and not from the grid. AC coupled systems do have separate dedicated inverters and transformers for the solar side, and then separate dedicated inverters and transformers for the energy storage side. And depending on the cost and whatnot, my view would be that this would actually generally be the more expensive solution by a bit, is to have these redundant inverters and transformers on the AC side. On the DC side, one of the advantages that you would have would be the ability to increase the amount of PV energy that can be delivered through the same interconnection. And I'll touch on that a bit more in the next slide, but the idea is essentially you can overbuild the DC portion of the plant and get more energy out through the same nominal number of megawatts. The DC also could have a simplified interconnection process because you have just a single inverter. It could be simpler to do that commissioning and finish the interconnection. And then the DC coupled also allows you to take advantage of the solar project DC-AC ratio, as I was mentioning earlier. One thing that is common between the both, but we should touch on here a little bit more, is that you can do all of the use cases, grid stability, T&D deferral, renewable plant stability, et cetera. You can read them here on the screen with both an AC or a DC coupled system. But when you DC couple the system, you do limit yourself in flexibility to some degree. So I agree with Vikas fully on that you do have some limitations on the use cases and on your flexibility, really, when you do DC coupling. Just to walk through a little bit the idea of maximizing the solar output when you use a DC coupled energy storage system. So a solar project that's built with a 1.3 DC to AC ratio has a bit of an overbuild, right? This is quite common in the solar industry today to economically optimize the plant. You put in enough solar that you have essentially clipped some of the energy during the peak part of the day, during the peak irradiance, because it makes sense financially overall to do that. Well, one of the things that you gain when you go to a DC coupled energy storage system is you can in fact increase that ratio if the economics work out for this to be advantageous, or you can increase it up to 1.8 DC to AC ratio, perhaps 2.0 DC to AC ratio, perhaps even a bit beyond that if it's something that's optimal for the project. And then the battery, rather than clipping that energy in the middle of the day, because the battery and the PV are on the same DC bus, you're able to capture that energy, and so it doesn't actually get clipped. You can just have it flow into the battery in the middle of the day, and then you can time shift it until another part of the day, and then you can dispatch it. You can dispatch it later. So in addition to just making the system become more dispatchable and a more flexible resource, you can in fact increase the amount of energy output for the same amount of interconnected megawatts. Wanted to provide one brief case study on that particular type of architecture as well. This is a project that's in Hawaii. This is a project from that's being developed by AES, which is one of the parent companies of Fluence. And this is a very interesting case, I believe, because the problem really that the customer, which is the local electrical co-op there, was trying to solve is that electricity in the island is quite expensive, and that's because fuel is quite expensive, bringing fuel onto this island. So essentially, they were willing to sign or able to sign a PPA for a solar plus storage facility that had a 5-hour duration. If you remember from earlier in my talk, 5-hour duration is getting into the range where you'd expect to do this if you were looking to time shift the energy and turn the system into being like a dispatchable solar type of use case. And that's exactly what they're doing here. So you could think of it almost as a renewable peaker that provides flexible but firm capacity to meet demand. So if you follow the graphs there on the right side of the screen, the blue line is the battery power. And in this particular graph, negative power is charging. So during the middle of the day, when the PV really ramps up, the battery charges, the state of charge of the battery increases, the battery gets more and more full. And then later in the day, when the PV power ramps down, that's when the battery kicks in and it provides additional power into the early evening and late evening into that portion of the load profile, and really provides extra value to the customer. And with that, I will stop. Thank you.
TJ, that was short and sweet. So thank you very much. Okay, guys, we have some questions in here. I've seen both TJ and Vikas have been answering some. So Vikas, can I ask you, from the ones that you've been answering already, what have people been generally asking? And do you want to make any comments perhaps that we can share with the rest of the audience before we start with these ones that are here?
See, there is one question. Right now everybody wants to hear about lithium ion, either NMC or LFP or LTO, whichever chemistry. So when people heard about advanced lead acid, it didn't go well. So why did we use advanced lead acid in our project in Nigeria? So capital availability is one of the criteria which may not apply to countries, in Americas, but to some of the countries in Africa, availability of capital remains one of the constraints. So in order to ensure that within that capital, we design a system which is able to serve the needs for the next 3 to 5 years. That was the need of the hour. Was there an ability to optimize further on LCUV? Yes, but due to the capital constraint, we had to stick to advanced lead acid technology to meet the purpose of that very application rather than going for lithium ion. So that is one topic I wanted to pick. Second, there are a lot of questions about which side of coupling is better. Is it AC side coupling or the DC side coupling? I think TJ also picked on the same. It really depends on the use case. If you are very sure, very particular about the application of your system, you can go for DC to DC coupling. But if you think you need some flexibility, it is better to go for the AC to AC side coupling.
Thank you very much. So there are two separate questions for the two of you. Let's start with TJ. One is about, TJ is asking you how many behind the meter projects Fluence has to date. So perhaps, and then there is another one for you, because that you can answer later, about your portfolio in the US. So let's start with you, TJ.
Sure. For behind the meter, the footprint for behind the meter for Fluence is primarily in Europe. That's coming from the former Siemens side of our organization, providing some of these critical power type of resources to commercial and industrial customers. I don't have the exact megawatt or project number on hand at the moment, but I would say yes, it is something where we have experience. It's mostly in Europe at this point.
And you have your own software to control the storage system, correct?
Yeah, that's right. So Fluence is a solution provider, which means that we procure individual components of the solution. We do engineering on the overall solution, and then we have our own in-house developed software that brings it all together and makes sure that it functions as a cohesive, functioning solution to the customer. And that means that we also have the ability to, to stand behind the solution with warranties and performance guarantees, because we do provide that full wrap, if you will.
All right, Vikas, and regarding your portfolio in the US, what can you
so
tell
I'm very
us?
happy to hear that. Stirling Wilson, we started in US last year, and right now we are building 50 megawatt 2 solar plants in US. But as of now, these are vanilla solar power plants. They do not have any energy storage coupled to them.
Thank you. There's a question here about oversizing. Is it 1.2, 1.3, depending on the ambient temperature? The efficiency of the PV panel drops a lot. I don't know whether either of you, TJ, you want to take it?
Sure. So in this particular case, right, we're talking about a DC coupled solution. That's where it makes sense to increase that oversize to a higher and higher degree. 1.3, I think, would perhaps be the minimum amount of oversize where you might want to do if you're trying to get more energy out of a DC coupled solution. I mean, in just some of the discussions that I've heard with other customers, I've heard that number pushed even higher. I mean, even considerably higher, around perhaps even the 2.0. But as the question sort of alludes to at the end of it, it does depend quite a bit on site-specific conditions related to radiance and temperature and whatnot. So there's no single magic number, but you could push that number even quite a bit higher than 1.3.
Care to give us the number exactly? How much higher?
Well, as I said, it could be even like a 2.0.
Excellent, because you want to add something, I can see.
No, I think I'll stick to what he just said.
Okay, so you like the daring of the nature. Okay, there's a question here for you. It says, because from my research, it seems that a combo flow and lithium iron in the future of energy is the future of energy storage. What did you think? I suppose they mean from a cost basis.
Yeah. So I think almost all of us, we know that the future lies with storage. And a lot of us also think that the way the prices are dropping for lithium ion, there's a high probability that it would be it would be one of the chemistries of lithium ion. But I would also like to add a word of caution. There are other technologies. People are talking about flow technology, flow batteries here in the chat box. If you talk about a normal solar power, which you have to make more dispatchable, and there is no other use case, even the flow batteries are very, very competitive as of now, and they are only going to get more competitive. So broadly, we can say that yes, the future lies with the energy storage. Which technology will dominate? I think only the time will tell which technology will dominate the scenario.
Sorry, I was just like, we have a lot of questions. Have you seen? Like, we're getting more and more, which is difficult for me. I haven't been able to read them all, but there was one here I wanted to ask. Okay, this sounds, I don't really understand it fully. You guys know I'm not an engineer, but it says, what is the delta in the investment to go from 1.3 to 1.8 ratio? This is supposed to be for TJ, but feel free, the two of you. Do you simply achieve this by utilizing DC coupled inverters? It's a question from Guillermina.
I'm happy to take it, or Vikas, would you like to take it?
Go for it. Yeah. You can take it with TJ, and then
sure. It's funny, you and I are picking almost the same questions off the list, so I think we must be in sync here. It's a good question. So once you have the DC coupled architecture installed, meaning you've made the investment on the bidirectional inverter, you have the DC to DC converters between the inverter and the battery, and then you have the investment around the battery container and the batteries themselves. Really, the additional investment to go from a 1.3 to 1.8 isn't not related to the energy storage portion of the system at all. It's related to the PV side, right? So it's it's more panels essentially, right? Is the delta in investment there. Now, I would say that when you sit down and you do your use case at 1.3 versus 1.8, you might decide that if you do a 1.8 versus a 1.3, you will just want more battery, right? Because you're generating more energy. So I would caution you that it's not quite as simple as just saying, well, it's just 100% the panels. You would need to really sit down and say, well, how much energy am I expecting to capture? How much energy am I expecting to want to time shift? So you may also decide that you want to buy a bit more battery, a longer duration, for instance. But from a fundamental electrical architecture perspective, 1.3 to 1.8 is really about oversizing the PV. The battery storage portion of it can be sized independently, you would say.
Because anything?
Yeah, just to add to what TJ said, if you only look at the cost of the solar plant, and the cost of the solar plant from 1.3 to 1.8 would come down by almost 7 to 10%, which is a huge number. So for $100 million plant, just by changing the AC to DC ratio by from 1.3 to 1.8, you may end up on a per watt peak basis, you may end up spending 7 to 10% less.
Thank you very much, because if you guys don't have any specific numbers, because if you're a guy, he's quite daring in those sorts of things and likes to talk concrete numbers. We know each other quite well right now. Okay, there is a question here that is quite general, but I'd like to ask you two. And there is another two that have pressed us, to answer live, but you feel free as well to bring up if you've seen any questions you want to answer. There is quite a few about your specific projects in Nigeria and in Hawaii as well. How much do you think batteries will drop in price over the next few years? I suppose when you're making your calculations, you have to consider some sort of price drop over time. So how does that work in your book?
Okay.
Yeah.
Okay, I think that's a difficult one. So if I talk about if I talk about lithium ion and specifically NMC or LFP chemistry, which is the most used chemistry as of now, we think for the next 3 years the price is going to go down at the rate of maybe more than 20%. And after 3 years, when we have enough scale, when you have larger systems in place, when you have larger supply chain in place, the rate of decrease will go down to 7 to 10%. So first 3 years, about 15 to 20% per year, and after 3 years, 7 to 10%. That's what we think broadly.
Okay.
I would add to that we've seen declines in that range historically over the last 5 to 10 years for sure. I think the question is to what extent will those declines begin to moderate? I think there are some other third-party forecasts out there that I would tend to agree with that does show those declines moderating in the medium term, perhaps into the high single digit year over year rather than the 20% year over year. I think the 20% year over year is largely behind us. I wish it was still continuing, but I expect it would be more like the high single digit year over year. And then there's another interesting trend at the moment where in the immediate short to medium term, due to some of the materials costs issues that the industry is seeing at the moment, some just manufacturing limits or mining limits, I guess you would say, on some of the key portions of the inputs, as well as the ramp up of EV demand, where there may be a portion where we see it slow even more than that before it ramps back up again. So it is a very difficult question. There's no one has a crystal ball to know for sure, but I would say anyone who expects it to be 20% for the next 5 years will likely be disappointed in my view. I would say we also may see a bit of a bifurcation here coming soon, where going through a channel that has access to preferred pricing due to its volume, I think could become ever more important as the factory capacity that these batteries for stationary tend to share with EVs, as those channels tend to get more and more bought up by some of the auto manufacturers. So that's another trend I see as well on the battery pricing.
Yeah, I was going to say, I mean, you could take a look at the Bloomberg New Energy Finance expectations and forecasts. The issue is a lot of that is based on, batteries for cars. So it's difficult to know, what's happening really in terms of the energy generation side. But we'll leave it there because it is true. We need a crystal ball. We don't have one of these handy at the moment. There's a question here that says, if you oversize the power of PV panels, the voltage will be higher than a standard PV site with no storage. Is this a problem? What happens with the demanding of active and reactive current, which are related with the minimum and maximum DC voltage? Because you're reaching for it. Go on.
Okay, so if I've understood the question rightly, so I think we are talking about the reactive power compensation, which is one of the requirements of the grid. So right now, if you have a normal solar plant, the plain vanilla solar power plant, we are meeting the reactive power compensation either by putting more capacitors or by putting more inverters. So now that if you have one more system, which is an energy storage system with a hybrid inverter, the part of the reactive power compensation could be met from the hybrid inverter which you're putting for the energy storage system. So on the solar PV side, you can choose to put a little bit of less inverters, and these inverters will be covered by your energy storage. So overall, you will save some small amount of money in the solar plant side of it.
Any additions, or are we good, TJ?
Just briefly, I think one way that I interpreted that question was how does DC coupling storage, how does that affect the ability of a plant to perform maximum power point tracking, or MPPT? And I would just like to add the comment that adding storage on the DC side does not hinder the ability to do MPPT. So essentially, the voltage on that shared DC bus would be determined by an MPPT strategy, the same as it would be for a solar only plant today. And then the DC to DC converter between the battery and that DC bus would essentially regulate that connection such that the DC bus voltage could move around as it needs to.
Right. So just a point here, someone saying Morgan Stanley predicted a drop of 45% over the next decade in the price of batteries. And this is specific to lithium iron. So just to let you know, we'll leave it here. I actually don't remember this, but it is very possible. It's easy to find anyway. Lifetime estimation of the batteries. You guys, how do you do it in your financial projects? How much lifetime are you estimating? Or a number of expected full cycles?
Okay. So okay, let me take that. Probably TJ can add to it. So you cannot obviously put number of years to the lifetime. Depends on the use case. Depends on obviously the total number of cycles, and more than number of cycles, the throughput of the total of the battery. How much kilowatt hour of power you are taking out. But a typical NMC can give you 5,000 cycles, and and if you go for LTO, it can give you maybe 7,000 to 8,000 cycles. But in terms of year, as I said, depends on the use case.
I would echo that for sure. That there's once again there's no single right number to put on this. It is something where you need to work with a trusted partner who understands these systems to really help you figure out, based on your use case, what the expected degradation would be, and then more importantly, what type of warranty and guarantee you can get both from that provider as well as can be backstopped by the battery manufacturer. So that's a good reason to work with somebody who has experience doing these systems. I mean, as a very rough rule of thumb, I would say you can use the general idea that a system will degrade about 20% over a decade. So from 100% to 80% over 10 years. But as was mentioned earlier, if the use profile changes quite a bit, I mean, that rule of thumb, you could throw it right out the window. But just to give people a rough idea of what the number is, it's that number.
Thank you very much. And another question for you, TJ, is regarding your Hawaii project. How did you find out that 100 megawatt hour, 20 megawatt hour for 5 hours is the optimal sizing to deliver the lowest LCOE? Sure.
Yeah, that's an interesting case because it was done closely in discussion with the eventual end customer. So it was not the developer sort of coming in and saying, AES saying, this is what it needs to be, this is what the number is, take it. It was a conversation, right, about what would be right for their particular situation, their particular grid, the problem that they were trying to solve. And I think that's something you'll find in a lot of these type of opportunities is you'll need to have that discussion to get to the right number.
Excellent. Okay, so I know that there is a lot of questions still open. Unfortunately, we're not going to be able to get to all of them. We need to go. You guys have taken a look. Is there anything else you'd like to add in terms of some of the questions that you've gotten? You can start with us, and then TJ can.
Yeah.
There's a bunch of them there for you, but it's just we don't have the time, unfortunately.
I think we have taken, as an overall theme, I think a lot of the questions have been answered. I'm just trying to go through them once again. But if you think there is anything in particular which we should answer, or Belen, you can raise
For
it.
example, it's saying here, are you using deep cycle batteries? I don't know whether this is something, hasn't really come up before. Is this a thing? Do we need to discuss deep cycle batteries? Do you hear me?
Yes, I can hear you. Yeah, that particular term is not one that I am used to hearing as being a particular type of battery. I would say for the type of batteries that are typically being installed for these type of applications, which are like an NCM type of lithium-ion battery. Yes, that they can be deep cycled. If you cycle them a little bit less deeply, you can help with the duration in the long term. But yes, they certainly can be deep cycled. This is one of the factors we look at in every particular opportunity is what the optimum amount of depth of discharge is.
So just the last question before I leave off, there is one extra thing here that I also, smart inverters, do you think the smart inverters will provide grid support by providing reactive power? So I've never also heard this smart inverters thing. Is this something that we need to know about?
I think I can take that. And see, even the present normal inverters, which are not as smart, even they are able to provide the grid support. So right now, when we design the plant, we are able to support the grid for the reactive power using the normal inverters. So yeah, the normal inverters can help the grid, and I'm sure if the inverters are smarter, they will still be able to help the grid.
Okay, well, thank you very much. Okay, there's been a lot of questions about the slides, a lot of questions about the recordings. Yes, you're getting those. So just really, we don't have a lot of time remaining. Just like to say thank you very much, Vikas, for your time. Thank you very much, TJ, for your time and for sharing with us this really great information. You guys, you have their email address and the contact details in the presentations. If you have any problem, reach out to us as well if we can help. And thank you for being here today. And I'll see you in the next session that we have. See you soon. Bye.
Thanks a lot, everybody.
Bye.
Thank you.